Here is our right-angled triangular lamina. We're going to get the moment of inertia of this lamina about the base, that is about the side of length B. So we assume that the mass is uniformly distributed throughout this, and we consider the mass per unit area in this calculation, because we're going to be taking strips and converting the mass of each strip, writing the mass of each strip in terms of rho. So big M is the mass of the triangle, and its area is half the base by the height. So again, the units of rho here would be kilograms per square meter, mass over area. Now we could take our mass elements as like tiny little squares or rectangles, but it's much easier to solve this problem by making our mass elements strips that reach from the left side of the triangle to the hypotenuse. Strips of width, well, we can say delta x or delta y. I'll just use delta x. Of course, we want to get the perpendicular distance of each of these mass elements to the axis of rotation. So that distance is x, and then we change x by an amount delta x to get the width of each strip. So the moment of inertia of this strip of mass delta m about this side here is given approximately by delta m times x squared. So that's the approximate moment of inertia. So we've seen all this before. We want to get delta m in terms of x. So as usual, to get delta m in terms of x, we use the fact that rho is the mass of any part of the lamina divided by the area. So delta m is the mass of the strip. We divide that by the area. Rho is constant regardless of what piece we take, of course. We just divide its mass by its area and we have rho. Okay, rho is actually equal to big M over half BA. Right, so what's the area of the strip? Now this bit is a little bit more tricky than the previous example of a rectangle, because as you can see, you know, the thickness is delta x, but what's the length of the strip? And the length is it's not actually in the shape of a rectangle, because it is curved edge. Well, it's not a curved edge, it's a slanted edge. This side here is vertical. But we won't actually worry about this slanted edge, because in the limit, as delta x approaches 0, the strip approaches the shape of a rectangle. Now we need to write the length L of the strip in terms of x. Now you might say I'm taking the longest side of the strip as L. What about the top side? The top side is shorter than the bottom side, but that doesn't matter. Again, as delta x approaches 0, the strip approaches a rectangle, so both top and bottom have the same length. So let's say, after we take limits, that the length is L. So we'd squash the top of this strip down, so the top will just coincide with the bottom of the strip, so we'll essentially have a line or an infinitely thin rectangle. Okay, well, we can use similar triangles here. Okay, you see that this triangle is similar to this one here. They both have the same angles. Okay, because with parallel sides and all that business. So we can take ratios of sides. So we can take ratios. Well, actually, we're looking at the tan of this angle in both triangles. So the tan of this angle is opposite over adjacent in the small triangle. So we can see that in the small triangle it's L over A minus X. Okay, so X is the distance to here. Since the total distance is A, it's just the total distance minus X in the limit when the strip becomes infinitely thin, of course. So opposite over adjacent for the small triangle equals opposite over adjacent for the big triangle. So that's how we get L in terms of X. B and A are just constants, of course. Okay, so we're nearly there. We have L now in terms of x. I just multiplied both sides by a minus x. To get the area of the strip, we multiply the side of the strip, which is L, by the thickness of the strip, which is delta x. So we just multiply rho by the denominator here to get delta m. So there's delta m in terms of x. So now we go back to our moment of inertia. So we have to multiply all the mass elements by x squared, the distance squared to the base, and sum all of those over all the strips running from x equals 0 up to x equals a. So this point up here corresponds to x equals a, and this point here corresponds to x equals 0, because the strip at the very bottom has distance 0 to b, and the strip at the very top has distance a to side b. Alright, so of course we just have to fill in, we just have to plug this thing in here for delta m. Okay, as I've explained many times before, this quantity is only the approximate moment of inertia about side b. That's because that delta x we haven't taken the limit as delta x approaches 0. Okay, so as delta x approaches 0, we replace the summation sign with an integral sign, which is just an elongated s, meaning we're summing. Now, b over a times rho is just a constant, so we can pull that outside the integral sign, of course. And we have a minus x times x squared. Well, that's ax squared minus x cubed. And as delta x approaches 0, we replace delta x with dx. Now, we're summing all the strips from the bottom to the top of the triangle, so we're integrating from 0 to the top of the triangle. So for x equals 0 to x equals a. Now, we want this in terms of m, so as we've seen many times before, we replace rho with the total mass of the triangle over the area of the triangle, half the base by the height. Now, this is an easy integral. Integrating ax squared gives us a third a x cubed. Integrating x cubed gives us minus a quarter x to the power of 4. The limits are from 0 to a. Okay, so multiplying above and below by 2 here, we get 2m over a. And 2m over a divided by a is 2m over a squared. So now we plug a in for x here. So we have a third a by a cubed, that's a third a to the power of 4. And we've minus a quarter a to the power of 4. And then we have minus sign, and all of this with 0 in, well, we're just going to get 0 if we do that. A third minus a quarter is 4/12 minus 3/12, which is 1/12. So we end up with 1/6 m a squared.